It is a great pleasure to introduce our next speakers, Sid Hariharan from CMU, and from EPFL, Maryna Viazovska.
Thank you very much. So together with Sid, we will speak about formalizing the 8-dimensional sphere packing problem. And so yeah, so this is about my introduction into the field of formalization. So I never formalized anything before. So and it's I think 2 years ago, Kevin Buzzard has visited the PFL, and he gave a talk about formalization, and he convinced me that I should try to do it. So I'm working on this homework he gave me, and so. Yes, so we decided to structure the talk. So first I will speak about mathematics behind the problem. So what do we try to formalize and how we do it? And then we'll speak about a little bit about the formalization itself. And finally, we'll speak about our experience of interacting with AI agents. And so, okay, so let me first introduce what is the sphere packing problem. So imagine that you have a very, very big box and infinite supply of equal oranges. And you try to put in this very, very big but still finite box as many oranges as you can. And then probably at some point you will realize that what is really, if your box is big in all dimensions, you will realize that what really matters is the density with which you pack oranges. So the overall volume of the box is what is important. And so what you really want to optimize is the density of oranges inside of your box. And so this problem is I like it because it's a very nice optimization problem. It is known to be difficult, and it also has a number of applications. And so what we are interested in is to finding these densest configurations of non-overlapping equally sized balls in d-dimensional Euclidean space. And in each dimension, there would be some supremum for this density. And this number, we call it the sphere packing constant. So this is the number which depends on dimension. And so now if we go over the first 3 dimensions, we can see an interesting pattern. So first in dimension 1, this is a trivial problem because a ball in dimension 1 is just an interval, and we can cover line with intervals essentially without overlaps. Then in dimension 2, this becomes kind of a curious, interesting, but not a very difficult geometric problem. And it was, so here the best packing in dimension 2 is the hexagonal lattice. And here is a visual, which is not an exact analogy, but you can see that even bees can pack spheres. And this is something the answer to this question was known, and even the proof of it was known, and since the end of 19th century, beginning of 20th century. And then some people who are very pedantic and want more formal, more rigorous proofs, they were pretty much satisfied by the middle of maybe by 1940s. The Feyerstoff gave a proof that satisfied people. And in dimension 3, it's known to be a very difficult problem. In dimension 3, we know that even though we know what is the optimal way to pack things in maybe since 17th century, when Kepler has analyzed these problems and his contemporaries, and even there are some earlier texts about possible solutions. As we know now that in dimension 3, the solution is not unique. There are uncountably many equally dense and non-equivalent packings, and the problem is very difficult, and it was solved only at the end of 20th century, and famously solved by Thomas Hales, and it was a very difficult computer-assisted proof, which later was formalized, which also gives this very nice historical connection between formalization and sphere packing problems. So now if we go to the higher dimensions, then we somehow we can always, even though in many dimensions we cannot solve the problem yet, but we can have this upper and lower bounds. And here in this curve, so the blue curve represents the best known densities that we know. Okay, so maybe not the best known of today, but to the time when I first time made this slide. And actually, there could have been some progress, but I think not in the blue curve. So the blue curve are the known examples, and this is a plot essentially taken from Conway Sloan book on packings, lattices, and codes and groups. And yeah, so the dots are connected by a line just to make it visually more to make it easier to read, but these are actually, like, of course, the known densities, they're only in integer dimensions. And the red line, it is one of the upper bounds, so-called Connell-Elkis bound that I will speak about later. So this is a bound obtained by linear programming. And so here what you can see from this plot is that, okay, so normally we have this gap between blue line and red line, which means that the problem is not solved yet. And there are some other things that are actually, we don't really see what happens in very small dimensions, the dimensions which I discussed before. But then we see that in slightly in the range of mid dimensions, we can see that the blue line and red line, they meet, at least visually, they meet in dimensions 8 and 24. And actually, they also meet in dimensions 1 and 2, but this is not so visible on my plot. And so, yeah, so this is the dimension 8 is the one that I'm going to speak about today. So, so my contribution to the field was to show that this numerical coincidence, that actually, and not a numerical coincidence, but a mathematical one, and that two curves, they actually intersect in this, at dimension 8, and then working together with my collaborators, we were able to prove the same for dimension 24. And so dimension 8, it's a very special dimension from various reasons. So, like different important mathematical structures that exist in this dimension which don't exist in other dimensions. And one such a miraculous thing is the E8 lattice. And so here is the coordinate representation. So this formula gives us what are the coordinates of one of the possible realizations of E8 lattice. And so it's an even unimodular lattice of rank 8. And its minimal distance, so the between 2 points in E8 lattice is square root of 2. And so this gives rise to, if we resize everything, this gives rise to a E8 lattice packing. So it's a packing of spheres where we take the points of our lattice, they are centers of the balls, and we make balls so big so that they touch each other but do not intersect. So what we do, we take the length of the shortest non-zero vector, and we divide this length by 2, and this would be our optimal radius of the balls that we are going to pack. And so as we can do this, we can compute the density of a resulting lattice, and so this is the number we will get. And so the theorem I'm speaking about today, it is this theorem. It tells us that the packing which we have constructed from 8 lattice is the best possible packing in dimension 8. And so the E8 lattice, it has a companion, there is another remarkable mathematical object which lives in dimension 24. This is a so-called Leech lattice, and the same way as the E8 lattice, it comes up actually not only in the sphere packing problem, but in many different mathematical problems. So does the Leech lattice. So it comes up, people discovered it by, actually it was discovered by engineers who tried to construct error correcting codes. So it came from error correcting world, and then it played important role in the group theory, in the discovering sporadic finite groups, and in discovery of the monster group. And it turns out that it's also a very, it was a good candidate for the packing. But the packing problem, and so the minimal distance between points and Leech lattice is 2, which is actually very beautiful because this time the minimal distance is 2, so we don't need to rescale anything. We just take these balls of radius 1 and to take them with to force them to have their centers at the points of Leech lattice, and we get this packing, which with radius of with balls of radius 1, and also the co-volume of this packing would be 1. And so this is the theorem which we proved together with Henry Cohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko. We show that the Leech lattice is essentially the best packing. It provides us with the best packing in dimension 24. And so now let me tell you a little bit on how this works. So these are these two cases when blue line meets the red line from the previous plot. And so this theorem, it tells us what that red line is. So this is a method which is called linear programming, and it's used a lot in geometric optimization. And it was adopted by Kohn and Elkis to packing spheres, and also independently by Dmitry Gorbachev, who developed a very similar method around the same time. And so what this method tells us is that somehow, probably because in the world we have this duality between like points and functions. And so here the idea is to go to this, if you want to say something about configurations of points, we will actually go to the space of functions and find a special element there, so special function, which satisfies certain constraints. And then the function which satisfies the constraints, it would be a witness proving bound for the possible density of sphere packings for us. More precisely, what the Cornell's theorem tells us, that if we suppose that we are able to construct a function f, and this function, it's a function which is from d-dimensional space to real numbers, and we want it to be Schwarz function. And Schwarz function means that this function is infinitely smooth. It has all the derivatives, and the function itself and all of its derivatives, they have fast decay. So the function and its derivatives, they decay faster than any inverse power. Then if we are able to construct such a function, and also wanted to satisfy some inequalities. So one of them is that we want our function to be non-positive outside of a ball of certain radius r0 centered at the origin. So our function is somehow, it could be a little bit, have some small bump of positivity around origin, but then it's non-positive. And at the same time, its Fourier transform has to be non-negative everywhere. And so these two conditions, they compete with each other. So it's actually difficult for a function to be both negative or almost negative, but also have positive Fourier transform. So it's not easy to construct functions like this, especially if we want R0 to be small. And then we somehow to make this actually to solidify this contradiction, we also want to normalize our function so that the value of function at 0 and the value of its Fourier transform at 0 equal to 1. And so when we are able to find a function which satisfies these three conditions, and so also in these three conditions, somehow the game becomes difficult if R0 becomes small. And then if we can do it for some R0, then we would know that the density of a sphere packing in dimension d is bounded by this number, which is the volume of a ball of radius R0 divided by 2. And so you can also see that somehow, of course, like now doing this for smaller radius is more like gives us more, it's a better theorem. And so how the red line on my plot originated? It originated by finding numerically constructing such Schwarz functions f for some values of R0, and the optimization problem would be to find this value of R0 as small as possible. So here's the idea of the proof of it. So the proof is actually quite simple, and it uses the properties of Fourier transform. So I suppose that X would be a discrete subset in Euclidean space, and we assume that any 2 points in this set, the distance between them is bigger or equal than R0. So this is somehow the candidate for the centers of our possibly good packing. And also here we make one simplification. We assume that this configuration of points is periodic with respect to some lattice. And so then we can write the following chain of inequalities. So here the first inequality, it will just follow from the first property of our function f. Then here is the trick comes that we are using Poisson summation formula. And go, instead of taking sum of values of f, we consider sum of values of the Fourier transform of f. And this is maybe the main actually tricky technical part is that we are rewriting our sum in this way. And after we have rewritten, we jumped from the third line to the fourth line. Now we can use the properties of the Fourier transform, which were required by Kohn-Elkys theorem, and we will get such an inequality. And so you see that if we compare where we started and where we have ended, so then this inequality will give us a bound on the density of points of the configuration X. And so because our configuration is periodic, so if you want to compute the density of X in the all Euclidean space, it will be actually enough for us to compute the number of points of X inside of a fundamental domain. And so this is how we obtain the proof of the Kohn-Elkys theorem. And so, okay, so I think I have. Okay, so here I think I messed up a little bit. So actually, what Gorbachev's theorem it was actually I have to attribute to Gorbachev the previous theorem and not this one. I apologize. So this is this was a typo. So, but this actually this numerical result it comes from the paper of Kohn and Elkys. And so using the previous theorem as a machinery, they were able to prove this bounds on the sphere packing constant in dimension 8 and 24. And so you can see here that this upper bounds, they are very close to the densities of the E8 lattice and of the Leech lattice. So essentially what they proved that if there is some packing in dimension 8 which is better than E8 packing, then it is only better by this like 0, 0, 16 and so this result is from 2003, and actually the computation was repeated later and they proved a lot. So here instead of 3 zeros in 2003, one could have like 60 zeros in 2010. So this is really like a numerical difference. And so, yeah. So what was again my contribution to the field was actually to find this this optimal candidate. So the best auxiliary function f, which satisfies all the best possible conditions of Kohn-Elkys theorem. And then we have done working together with Henry, Abhinav, Steven, and Danilo. We have done same thing in dimension 24. And so this is how the function looks like, if you want to know how this function looks like. So, and maybe I want to say that this function, which proves the sphere packing problem for us, so Steven Miller suggested calling them magic functions because they kind of do difficult work for us. Yeah, so here what can we say about this function? So this is how this optimal function look like. And maybe there are certain things we can say by looking at the plot. So first, the Kohn-Elkys theorem, I promised you that we should construct a function from R8 to R. And so but here is one-dimensional function. So what happens? Okay, so what happens that it's actually natural to think of our function as being radial. So for our magic function, we can assume without loss of generality that it is a rotation invariant around origin. And why is it so? It is because all the constraints in Kohn-Elkys theorem, they're also rotation invariant. So if we have one magic function which is not radial, then we can always rotate it and average over all the rotations, and we will always get a radial function which satisfies all the same constraints. And so, of course, it's much nicer working with one-dimensional functions than with 8-dimensional. And so another thing which we can see here is that, okay, so here also I promised you a Schwarz function, and it is a Schwarz function, but so to visualize it, I had to multiply my Schwarz function by a Schwarz function which grows very fast. Otherwise, we would see only like the small bump, initial bump, and then everything would be visually 0, which is maybe not so interesting. And as we do this renormalization, what we can see that this function has a lot of double zeros. And so these double zeros, they're also not accidental, and they are a consequence of satisfying the Kohn-Elkys condition. So we see that in order if our function is optimal, it means that in order for all our inequalities of a previous theorem to be equalities, the only way it can happen is if our function and its Fourier transform vanish at all vectors, or at all numbers which are lenses of some non-zero vectors in E8 lattice. And the lenses of vectors in E8 lattice, they're all square roots of positive integers. And so the last important ingredient is that now we have to construct a function. And so here I take it a bit like out of nowhere. So what I would like to do, I would like to construct this magic function in the following form. So for example, when Kohn and Elkis worked on their theorem, so their numerical solutions to Kohn-Elkis optimization problem, they were constructed in the form that the function took a form, it was a polynomial times a Gaussian, and then it's easy to compute the Fourier transform of this function explicitly. And so this is how they got very good numerical approximations. But at the same time, if our function is a Gaussian times a polynomial, then we cannot hope to have that many double zeros. That would be just impossible. So we need to search to make some other assumptions about our function. And so here I would search for our function in this form. So it would be sine square, which creates all the double zeros that I need, and then a Laplace transform of something, which I do not specify yet. And so I want, again, no, it's not very motivated, but I would like this function under the Laplace transform. I want it to be, I think of it as first as a function which is not on the real line, but rather on the imaginary axis. But I also want it to be extended to the complex half plane. And so here I don't tell you why I do this. I have my reasons for that. But then if we do this, what turns out? It turns out that this function phi would have some hidden symmetries. And this would be symmetries of a modular group acting on the upper half plane. And so the function phi, I will search for it in a special class of functions vaguely called modular forms, and functions which are similar to modular forms. So I would want this function phi to satisfy the following symmetry conditions. And so and where this and so the advantage of this is that this way it will be easy. So I have my, maybe just like I want my function to be in this shape, but also when I take the Fourier transform of f, I want to have at least a hope that after I take a Fourier transform, it will be a function which can be written in a similar way. And so this is where the modular forms are coming from rather naturally. And so this is where the action of the modular group is coming from. And so we have to work with this function. And advantage is that this function actually well studied. There were other classical objects studied at least since 19th century. And we know a lot of facts about these forms. Also, we have effective ways how to compute, how to calculate with them. And so, yeah, so here somehow like this condition which I gave here, it's a bit too restrictive. I would have to relax it in several ways. So one of them, I want my function to be, allow it to have poles, not at the upper half plane, but at the boundary of the upper half plane, and or to be so-called weakly holomorphic modular form. And so here are the examples of this modular forms, and a classical one is Eisenstein series. And maybe what is important for us is that for Eisenstein series, we actually know their Fourier transform. Not Fourier transform, sorry, Fourier expansion. And so this is how what makes it very easy working with this function numerically. But then for everything to work, the modular, also Eisenstein series, which are modular forms, are not enough. I need this another exotic object, an interesting object called Eisenstein series of weight 2, which is a quasi-modular form. And so this Eisenstein series of weight 2, it does not exactly satisfy my transformation properties, but it satisfies them with some correction term, which is also easy to describe. And so these are other types of functions which need the classical theta functions. And so the nice thing about theta functions is that again, we know that they are modular forms, but we also know their Fourier expansion very explicitly, which makes it easy for us to work with it. And so now, after we have all this, so now what we are going to do, we have all these objects, and we are going to create new functions out of them by considering polynomials or rational functions in this in the modular forms. And so by searching this space of modular forms, we are able to find these two functions, which will allow me to create the magic function. And so again, because these are modular forms, I can first compute as many Fourier coefficients of these four forms as I want, and also I know, for example, how fast coefficient grow. I have control over this, so I can do analysis with this function in a very quantitative way. And so now the theorem is that this function, which is defined above, this would be the magic function that we need. It will have all necessary properties of the Kohn-Elkis theorem. And so now, first, after we have constructed the function, just what we have to do, we have to actually prove that the function G satisfies all the desired properties. And so here are important steps. So first is to define the function to prove that the integral is well defined. Second one is to another step is to compute the Fourier transform of the function. And as I told you before, so that the function G was specially designed so that it would be easy to compute its Fourier transform and to express it in a similar way, where we again have the sine squared, which guarantees us double zeros, and multiplied by a Laplace transform of a certain function. And so now, after, if you know the function is well defined, its Fourier transform is well defined, what we need to do, we need to prove that all the inequalities of Kohn-Elkis theorem are also satisfied, inequalities and equalities. And so these are also the parts that we have to check. Yeah, so this is the mathematical structure of the proof. And so now we can come to the formalization part.
Right. Okay. So as a fun fact, before we get into the formalization stuff, you see how the form in which we've expressed the magic function here involves sine squared. And if you actually look at the blueprint, the way that we've defined the magic function is quite different. So the project that I proposed for the working group here is to precisely connect these two definitions. Just as I thought I'd mention that. Okay, so just a brief history of sphere packing in Lean. We have a website, which you should definitely check out if you want to get involved in this project or if you want to stay updated on our progress. And the way that this project got off the ground is, as Maryna mentioned, Kevin Buzzard was visiting EPFL. Around the same time, I was an exchange student at EPFL, and I was coming from Imperial, so I knew Kevin already. I went to say hi, and then that's how we got the project off the ground. So yeah, I mean, I think, over the summer, I worked on some of the basic sphere packing theory along with Gareth Ma. And then all of last year, I worked with Bhavik Mehta on some aspects of formalizing the construction of the magic function. And on the 13th of June, we took this project public at Big Proof. One development that maybe not everyone here is aware of is that on the 19th of October, we launched our first packathon. Now, what these packathons are is that they're just weekly meetings which take place in person at the Hoskinson Center at Carnegie Mellon and on Zoom, so anyone can join. And the idea is just to get together and pack spheres. So we talk about, we talk about progress. We share we share updates on whatever we're working on. We review PRs, we do this sort of thing at the packathons. So if you want to get involved, the best place to do this is the packathons. So Mondays, 11 a.m. Eastern time, they'll resume in January. Okay, I'll talk a little bit about, we have a blueprint which you can find on our website, but I thought I'd share a blueprint of a blueprint. So an even more high-level overview of the structure of this project. So we have this basic sphere packing theory stuff, which is, densities. What is the sphere packing? What's periodic packing, density, stuff like this. Facts from Fourier analysis, including the Poisson summation formula and general results about Fourier transforms. So we have a PR in the works that proves the Poisson summation formula in n dimensions, which does not exist in MATLAB. So if you're interested in looking at this, I think it's PR 157, but if you just look at the PRQ on the sphere packing repository, you'll find it. Cornell keys. So interestingly, we've been making a lot of changes to Cornell keys. I worked on Cornell keys in summer of 2024, but we've recently started refactoring this to use the complex partial ordering and some stuff like this. So I don't want to get into any technical details, but yeah, there is some interesting work happening on Cornell keys. Now, it turns out that for the construction of the magic function, and more so to prove that it satisfies the properties you want it to satisfy, you need a lot of results about contour integration. And Maryna will talk about that in just a minute. But contour integration is famously difficult. Alex Kontorovich talked about it briefly yesterday as well. It is famously difficult to do in Lean, but we have some ideas, and we're making some progress there. Basics of modular forms. This is largely the work of Chris Birkbeck, which is also partly, he's been a close collaborator of ours, but he's also built a significant chunk of the modular forms part of MATLAB. So he has independent interests here as well. And I'm working on the construction of the magic function. Hopefully this week at Italine, we can make some progress there on the 00 stuff. And then we have the proof of the inequalities, which is, we're formalizing a different proof from Maryna's original one, a proof by Siwoo Lee, which again, we'll talk about briefly, very briefly. And finally, we put all of these ingredients together to get the main theorem. So some recent progress is we managed to show, so these things have been green for a while, but at big proof, this one was not green. Now it is. So in other words, we've managed to show finally that the E8 packing has density equal to this number here. This is important because this is what we will eventually show to be equal to the Cornell-Keys upper bound corresponding to the magic function. We've also done some work over here, but this still remains, this is a rather important, which Yale was working on for a time. So if anyone is interested in contributing to this, I would suggest getting in touch with them. And yeah, so this is a rather important step in Cornell keys because it allows us to simplify the problem to one of showing that really the densities of all periodic packings are bounded above by this number, and that's enough to show that in fact the densities of all packings are bounded above by the Cornell keys thing. Fourier analysis and the Poisson summation formula. So this stuff above here exists already, and as I mentioned, we've been making a lot of progress on Poisson summation. So we decided to shift gears a little bit. We were initially trying to prove Poisson summation in n dimensions by induction on n, but recently we decided to take a slightly different approach, which is to kind of go directly from sort of just look at how it's done in one dimension. We have a one-dimensional version in MATLAB, which is where you sum over z in R. We don't even have an arbitrary lattice. We just have z, but it's not that difficult to go from z to an arbitrary lattice. So we're trying to prove it for z to the n in Rn, and then from there it's not too difficult via some linear transformation to show it for an arbitrary lattice. So the approach to show it for z to the n in Rn is being led by Aaron Lin, who's a first-year PhD student at Carnegie Mellon, like myself. So this is actually where the idea of the packathons was born. Aaron and I got together one evening with a couple of other people at CMU, and we decided to brainstorm and hack away at this. And we figured, why not do this every week? So yeah, join the packathons. And formalizing the Cornell keys and Gorbachev linear programming bounds. So this is really these two ingredients together allow us to formalize Cornell keys. And we've done Cornell keys modulo these two ingredients. So if we can do these, then we'll be done with Cornell keys. So we really need some help with these. So if you're interested, if you're looking for something, if you're looking to get involved in this project, definitely reach out to us and we can help you get started on these. Okay. Maryna will talk a little bit about contour integration, and then I'll talk about AI.
Yeah, so if you remember the, maybe let me just go back quickly to this slide on general structure of the proof. So here you can see that somehow contour integration is a very important ingredient because it's like it's very much on the top, and then there are many things below that depend on it. So the contour integration is needed to first to the function is defined as an integral or contour integral of something in the of a function defined in the upper half plane. But then if you want to prove that this function satisfies the conditions of Konelky's theorem, we use a lot of manipulations with contours to do this. And so it was an important part of the project to fix this part, and then it unlocks possible progress in all the directions below. And so as our first, what was known before our project is the Cauchy theorem for rectangles, for rectangular contours. So this already exists in MATLAB. But our contours are more like we needed to do more complicated things. And the first thing we needed, this is what was already adopted, is that our contour it's not compact. It's infinite. So it's an infinite half line. So we needed some kind of like an unbounded rectangle version. So this is what Sid and Birkbeck have developed. But unfortunately, this was not enough. We needed more. And for the all manipulations with contours which we want, we realized that, okay, so maybe the minimum that we need is a contour like this. So this is the contour we need. But then, so this was something, this was the slide we presented in the big proof in summer. But since then, actually, I don't know, I probably started remembering how I studied complex analysis and had a bit of an epiphany about this. So like what we were trying to do before is really to prove Cauchy theorem for various particular shapes of a contour. But then when I had memories from my undergraduate studies, I remembered that actually shape of the contour is not all that important. And that maybe we can change our direction a little bit. So what is maybe more important is the shape of the domain where a function is holomorphic. And if this shape is simple, then the contour could be anything inside of the of this domain. And so this, I believe that this is the right way, instead of proving Cauchy theorem in this form, where he's actually from an analytic point of view, it's a quite complicated thing. What we want our function to be holomorphic only inside of the contour, and also have some boundary conditions on the contour itself. And this makes things complicated. But actually, the functions we are working with, they have there is a much bigger domain where they are guaranteed to be holomorphic, and this could simplify everything. So here maybe our philosophy has changed, is that we could prove this Cauchy theorem for any, for example, convex domain, and inside of this convex domain we can allow any contour. And so this theorem actually they already exist in Isabelle. And we also worked together with Auguste Poirot to formalize the first theorem of these two in Lean, and we have succeeded with that, but with only one small difference, is that we did it for unit disk, but not because it's much simpler, but just because at that time we did not somehow realize that this is maybe an easy way to go. And yes, now I hope that now when we had this realization, it would be easier to formalize these two theorems. But then, of course, to have the actual result that we need to somehow. Unfortunately, life is not because the contour that we're integrating it actually touches the boundary of the domain. So we also would have to do some dancing around the boundary. And then hopefully the contour integration will be done, and it will unlock new possibilities. And so, and then it could go. Let us go further along this tree where we construct and prove important properties of the magic function. And so maybe before I switch back to Sid, I would like to a few words about another important contribution, an important that make us more optimistic about the success of the whole project is that in the original proof it requires proving certain inequalities for very concrete functions. This function a of t and b of t. These are two functions defined on the half line. So the way I proved originally these inequalities, it was by because I knew these functions approximately. I knew their Fourier expansion somehow at the cusp at infinity and also at cusp at 0, so I could approximate functions with their truncated Fourier expansions and prove some analytically prove some bounds for the difference, for the error term. And so this is how inequalities were proven originally. But you know that in Lin doing such things is difficult. It's difficult to convince Lin trusting numerical computations. And also maybe this method is not very elegant. So two other fixes for this were analytic proofs of inequalities were suggested. For one proof was suggested by Dan Romnik, and another was suggested by Shivu Lee, where they prove same inequalities but with somehow without this extensive numerical computations, but like with a few, I would say, human-sized smaller computations. And so now we currently plan on implementing the strategy by Sivu to. So this now his inequalities are already in our blueprint and now waiting to be formalized as we move along our tree. So and so then I switch back to you. Give my microphone back to Sid.
Right. So as you can see, there is a lot going on with this project. It is absolutely massive, and it is. I mean, we've been working on it for what, about a year and a half, more than a year and a half now. And we've made pretty decent progress, but a lot has changed in recent times. So I gave a talk about this project 2 months ago at Cambridge, and I talked about the project, the progress, what the contribution process was like, and the thing is, a lot has happened since then. Namely, these and a whole lot more. Right? There's new ones coming up every single day. So we had Aristotle. We had Aristotle go public with the API key. We have Gauss. The alpha proof paper dropped, and we have Axiom. We have I don't even know all the names. There's so many of them, and this has caused us to rethink a lot of things, such as the pace of this project, by when we expect to complete it, what the contribution process looks like, and things like that. And the truth is, we don't know what these things are going to look like anymore. But I thought I would take this opportunity to maybe highlight some of the contributions by AI, some things that AI has done well, some things that AI has not done too well, which maybe still leaves some hope that human formalizers are still relevant. But well, I mean, overall, I think our experience interacting with AI has been very, very interesting. And we've been engaging with Harmonic, we've been engaging with Mathink, and we hope to engage with more AI players as well to try and get them on board, because we are quite curious to see how well machines can pack spheres. So one thing about AI, right, is that they sometimes use not the best means to close goals. In other words, they exploit bugs. We've seen some instances of this. And it was actually quite interesting to find one instance of this in a recent PR to our project as well. So we've been running a lot of experiments with Aristotle. And there was one lemma that we wanted to work on, which is this lemma about smooth even functions. So if f is a smooth function from R to R, and it's also even, then one can show that there exists a smooth function g such that g of x squared is equal to f of x for all x. And we one contributor who was interested in working on this wrote an outline for this file, kind of a sketch proof with stories in it, and said, hey, why not run Aristotle on it? Let's see what happens. And Aristotle did a pretty decent job, but it closed some of these goals by setting max heartbeats to things like 500,000 and a million, which, max heartbeat should never be that high. And there were also a number of exact question marks, which I think that at some point this did something to the kernel, and that's why it built. I don't know. But if you look at a proof like this, you'll see that, yeah, there's just a big exact question mark there. And you can see that max heartbeats here is, what is that? I think that's 500,000. I can never count how many zeros follow a number, but that looks far too high. And this was quite interesting. But I will say that at the same time, it looks like the way that Aristotle approached this problem, that was something that we found quite interesting. So we gave it maybe 9 lemmas in an outline file, like 9 intermediate lemmas before the main result. It kept 3 of them and it overwrote the other 6 and it replaced them with, I think, a total of 13 or 14 lemmas, which it stated on its own. And we did not provide it with a link to the original paper. So the paper that proves this result about smooth even functions is a 1940s paper by Hassler-Whitney. We didn't give it a link to the paper. We didn't tell it that such a paper exists. We gave it no guidance apart from the 9 lemmas in the outline file. And it just overwrote a whole bunch of them. It restructured. So it somehow had some idea from the looks of it of how to proceed. It just didn't know how to close the goals, or it went about closing them in a rather unsound way, which is unfortunate. But it's still interesting. I think this is maybe the longest PR that we got that was written by Aristotle. Very, very interesting PR overall. So yeah, this is something I wanted to mention. The thing is, AI written proofs also sometimes expose bugs. We'll come back to this. We'll have time for questions later. So we had AI proofs exploiting bugs. We also had AI proofs that exposed bugs. So the thing is, AI seems to trust humans a lot. It seems to trust that the code we've written in our repository is good, which is flattering. But if I've made a mistake, I'd like to be told that I've made a mistake, because the thing is, I don't trust myself. So what happened is there was an interesting PR by Gauss, PR 181, where there was a certain result that I had to prove, where we had there were a bunch of parameterizations. We have 6 things called I1, I2 up to I6, and they have these parameterizations Z1 up to Z6. Now, in this case, we're working with, I guess in this case, J1 up to J6. And in this case, what happened is that over here, I've used the parameterization Z3, but here there was a typo. I meant to write Z3 in my definition of something, but I had typed out Z1. And Gauss still managed to prove this, except when it exploited a mistake in my definition, which is my bad. But I just found it very interesting, because then I was able to the way that I identified that there was something wrong with my definition was by inspecting the proof. I looked at the proof and I said, well, something seems off about this. It seems to use facts about J1, which is not how I would have done it. And it seems to be quite a bit shorter than I thought it would be. So putting all of these details together, I went line by line, and I noticed that it was in fact exploiting mistakes that I had made. So in this manner, I think AI written proofs can sometimes help expose bugs as well, even if they don't point them out explicitly. Yeah, I don't know. I thought this was interesting as well. Finally, sometimes they identify bugs outright. And this is something that I think Aristotle is quite good at, because it seems to run on both, it seems to try and prove both a statement and its negation. And sometimes it's good at finding counterexamples, is my understanding. And so Aristotle discovered a misformalization and Gauss fixed it, which is quite incredible when you think about it. So there was an issue raised by Lawrence Wu, where he pointed out this misformalization, which Aristotle discovered by finding a counterexample, and then Gauss managed to fix it. So this is the issue, which is maybe a bit difficult to read, but it found a misformalization in something, and then Gauss fixed it by essentially adding a hypothesis that was missing. The thing is, though, the reason why the statement was misformalized is because we were dealing with something called R, with a variable R, which was meant to represent the norm of some vector. Now, you and I, now everyone in this room knows that the norm of a vector is always non-negative, except I'd forgotten to specify that in my hypotheses. So that's why Aristotle was able to find a counterexample. And it was able to say, well, actually, you need something like this. You need a non-negativity assumption when you're working in terms of R. When you've composed with the norm, you're fine, but when you haven't, you need this assumption. And if a human had worked on it, I'm sure they would have spotted it too, but Aristotle just, I don't know, it spotted it as well, which I thought was quite incredible. The funny thing is, though, the fix by Gauss was to add a hypothesis that R was greater than -2. And I thought, I mean, this is technically correct. If R, I mean, but when is the norm of a vector going to be -1? So I thought this was a very interesting fix. It works. It's technically correct. And yeah, but I just find it interesting that this was the fix suggested. I don't know. I guess machines are very different at approaching these things than humans. So yes, the bottom line is the contributions. We've received a number of contributions from Gauss. We've received a number of contributions from Aristotle. We've merged a number of them. Some of them are still under review. Some of them are being golfed. This PR about smooth even functions, it needs a lot of work. We can't have those kinds of heartbeats. We can't have exact question mark. But I think overall the approach is still pretty decent in that PR. So I think it's worth working on and trying to maybe iterate a few times with Aristotle. So it seems to have been a very interesting experience, and I think it's been very insightful to get these contributions and to engage with these models. They're just sometimes a bit strange. I don't know what to say, but that doesn't make the contributions any less valuable, and that doesn't make the contributions any less interesting either. I think we live in interesting times. I think. I don't know what there is to say more than that. So all I'll say is, whether you're human, whether you're machine, or whether you're somewhere in the middle, I mean, I know that there are some people in this room who don't sleep very much and who keep making PRs. So I would say maybe they're somewhere in the middle. Extraordinary people, really. And yeah, just know that your contributions are valued and welcome, regardless of whether you're made of carbon or silicon. And yeah, join our project. Thank you.
Thank you very much for this great talk. We have time for questions.
First of all, thank you so much for this wonderful talk. So I have done a little bit project on this topic. It was pretty new when I have studied about that. So as we know that for dimension 1, 2, 3, it's fine. But when it's come to higher dimension, why particularly 8 and 24 like even? So in future, is there a chance can we deal with the odd dimension as well?
Yes, I think so it seems that somehow the sphere packing problem in each dimension is like a new game. And yeah, so of course always there is hope, and there might be things we don't know yet, but at the moment it seems that even the existing proofs, they all quite different, they all use different methods. So what I think maybe what might be more realistic is that maybe as computers get better, computational methods get better, maybe it would be possible to have like an algorithm solve sphere packing problem in dimension, and then you could solve it, I don't know, in dimensions up to 100. Or this I think is more realistic than finding way which like works in all the dimensions divisible by 8, because here like being even or being divisible by 8, it seems like it is an important factor, but it does not translate, like it doesn't generalize very well to like things that work for 24, they don't work for 16. So here probably there's 8 and 24, maybe there is something more going on, something more. Yeah. So it's kind of a miracle, and yeah, which probably doesn't reproduce, probably.
Yeah, thanks for the talk and great project. I was wondering about the following. I mean, this is, I think, an example where the formalization doesn't capture everything in the process of mathematical discovery, because I mean, these magic functions were found somehow, right? I mean, and I assume that there was like probably some also numerical exploration involved in that. And I mean, this gets lost when you formalize just the proof of this magic function because it like comes from heaven somehow, right? So I was wondering if it was possible or like it would be a good idea to also somehow write down or explain to the computer how these numerical explorations were made, and I mean maybe just put the source code somewhere and teach. I mean, if you think about, I mean, of course agents can be helping in auto-formalization, but if you want the agents to be also helping in finding those new structures, then they should have examples of how these discoveries were made, right?
Yes, I think it's possible. I imagine that the number theory should be somehow, there should be many examples like this. So again, like number theory, it's my area of expertise, but also, yes, I think some of these ideas can be automated and can be reproduced. But then, of course, we automate one type of idea, but then a new type of idea comes, and yeah. So I think there is a lot of space to explore here. So there is like one interesting project about this is, maybe you've heard of this, murmurations of elliptic curves. So it is like a phenomenon number theory, which was somehow like discovered by, yeah, maybe it's not would not call it AI, maybe it's closer to like data analysis, but then also a lot of data is computed, so number theoretic data, if we can call it like this, and then patterns can be discovered in there, and then later they are explained by mathematicians, when explained by the theory. And so I imagine that things like this, there could be more automation in it, but yeah. I also think it's like a big field to discover, but again, but I also hope that even if agents become good in it, then people could always come with some kind of new wild card to like newer ideas.
Hey, thanks. Yeah, thanks for the great talk to both of you. I was curious about the description because somehow an exploit and not a valid proof. Every case I'm aware of, it's not proof, and so I was wondering, use somehow or something that is made this proof.
Sorry, maybe you can repeat the
Yes,
so
let's try. Yeah. Okay. Yeah. Sorry. I'll pick then. Thanks for the talk. I think the microphone is kind of. So.
You want to just shout?
Yes. Thank you both for the very good talk. Appreciate it. I was curious about this exact question mark thing. Like every time I've seen exact question mark used, it's been sort of valid. You know, it pulls a theorem from the environment. It could be a local lemma, or it could be like a hypothesis, and it uses it. And it's a bit ugly that they remain in the proof, but like normally they are kind of just actually fine proofs. I think a lot of people, don't like them, and I think that's fair enough. You should probably replace them with the thing that you click on. So I was curious, was there something here? Was there like axioms used under the hood? I was a little bit confused, like what made these specific ones not valid proofs?
That's a good question. So the thing is, there's no axioms or there's no weird stuff under the hood here. I think what's happened is just that there's a very large number of them, and kind of, I don't know. I think we need to investigate this a little bit more. But for some reason, it doesn't seem to be building. There just seem to be a lot of. I think it's the number of them, because there's I think like I mean, there are some lemmas with maybe 4, 5, 6 exact question marks in them. Some of them are nested repeatedly. So you have like a rewrite where you have a lemma where you have, you have to feed in hypotheses, and those hypotheses are by something, something, something exact question mark. And then there's another sub goal, which is like an exact. So there's sometimes like, I think it's the number of them that are stacked into a single lemma. But I think it would be nice to chat about this and try and troubleshoot, because it seems, I don't know. I found this very interesting as well, because we've got many PRs by both Aristotle and Gauss, and none of them have done this. So I thought this was quite interesting. But yeah, I mean, I think maybe it's just, maybe there's just something minor that we need to fix, because by and large the proof seems okay. It's just that there's, I don't know, there's something wrong. I'm not quite sure what it is. Yeah.
So I can clear up a little bit on that. So that was discovered on Zulip, I think, with an I think it was in DeepSeek AI that learned to exploit this bug and got a better score on a benchmark because of that. So there was a bug in the lean kernel for some short period of time that was fixed quickly after. And it was where apply question mark, like a proof with apply question mark that had, I think, more than 500 suggestions would not have an explicit error, even though to the human it's clear that it wasn't a proof. But that has been fixed since then. So maybe the AI just learned on that and yeah. I actually have a short question. What are you going to do with your code? How can much of that make it into Mathlib? Because I care about things being in Mathlib and not just in your repository.
That's a fair question. I think we've been a bit slower than we should have been in upstreaming some of these things. But I also will mention that maybe a good, I don't know, 70% of it is maybe unsuitable, or maybe not 70, maybe that's too high of a number. At least when I talk about my part of the project, the construction of the magic function, there I think that's maybe a fair number because most of what we're doing is very specific to these functions. Stuff about modular forms is actively being upstreamed. Stuff that Siwu is working on quasi-modular forms, I think, I mean, I can't really speak for Siwu. I think there's some stuff being upstreamed, but not a lot. I think at this point, it's still a bit unclear. Yeah, Poisson summation definitely will go to MATLAB, but we haven't finished it yet. So once we do it, we'll go to MATLAB. And this unbounded Cauchy-Gauza stuff, we've got like, I think 4 versions of it in the repository. We're not sure what version is good. So we want to try and use it. We're using it for one of our results. And I think once we use it, we'll know which versions are actually usable. And that'll, I think, give us some idea on what to PR to MATLAB. But yeah, I think there's a couple of things that we should be PRing, which we haven't done yet. So yeah, our bad, but we will.
Hi. Over here. Sorry. Great talk. Thank you so much. It's so fun to listen. I was just going to clarify something that Michael said. So the exact question mark piece of this, when it finds a valid exact question mark to, so you could imagine other related bugs that elaboration time takes with the heartbeat stuff interacting. So if you have a string of exact question marks and it's getting close to the elaboration time that's allowed, maybe this is something you're seeing as well. Just to clarify, because it seemed like there was some questions. They are valid proofs. It elaborates into that particular search result, notwithstanding the apply question mark stuff been fixed. So
okay, that's interesting. Yeah, I mean, there's something going on here which I don't quite understand. So yeah. Sorry, I think we had a hand there first. But
thanks for the talk. I just wanted to clarify on that same vein, just to make it very clear, exact question mark is not part of the kernel. There's no kernel bug there.
is not part. Can you repeat that?
Part of the kernel. Exact question mark is not part of the kernel. This had nothing to do with kernel behavior, which was mentioned not by you, but by a previous question or remark.
Okay, maybe. Okay.
So then we'll come back again.
Exact question mark generates a term, and this term will be checked by the kernel. The proof is almost certainly not unsound. If you're seeing an error, the most likely issue is that you're running out of heartbeats. And exact question mark does a very expensive algorithm looking for potentially very large expressions. It can happen that it times out and you get an error, but this does not mean that your proof is unsound or anything. It just means it ran out of time and Lean is trying to protect you from running forever.
I see.
There is no unsoundness here, almost certainly.
But that's very good to know. That's very good to know. Yeah. It makes our lives easier when it comes to troubleshooting this PR and actually getting it into a mergeable form.
Hi, thanks for the talk. My question is not regarding lean. I was more curious about another possible approach, like regarding the curve that you show about cone Elkis, and the difference between like what is believed to be the best and what actually is known to be the best. I mean, I was thinking like you recently wrote a paper about modification of alpha evolve.
About, sorry, what?
A modification of alpha evolve. You were on that paper.
Yes.
Yes. So the question is like if you have some intuition in some dimensions, since if there are some properties of geometry of the plugin that can help the search of half evolve, and maybe like can allow to get a better signal to the LLM so that you can find better plugin that can close this gap.
Yes, but we actually we have not applied it yet to sphere packing in Euclidean, like alpha. We haven't applied it to sphere packing in Euclidean space. We have applied it to other optimization problems, but also here I think actually like this blue curve, I think it's like at least in this for dimensions, like for small dimensions I don't know, up to 24 or maybe a bit more. I think it's actually believed that these are the best packings. And okay, maybe after 24 there is a bit of less of a confidence. And so I think right now actually it's more plausible that this red curve has to be changed, and this is somehow far away from the truth. At least like in small dimensions, I think there is a lot of confidence that at least like up to 10 definitely that we do know all the best packings, or the candidates for these best packings, they're actually the best. We just cannot prove that they're the best. And so this is the red curve, which has to be changed. But then, of course, yeah, maybe if it's around 40, then maybe, yeah, maybe computational, maybe it's maybe there's something we missed. There are actually better configurations, which we have not seen. But yeah, so as the way I know about it, that in the Euclidean space, it's actually the computational methods don't give that very well results yet. So here probably there is a way for, like, there is room for improvement, but yeah. But also probably it would not be very easy. Probably this seems like a computationally expensive problem.
Okay, I suggest we postpone all other questions to lunch and thank again Maryna and Sid.